Hello everyone, welcome to Leankon's knowledge sharing series. In this video, we're talking about NFC antenna design, specifically how proper antenna matching can make a big difference in the performance of the NFC reader. We'll walk you through the key ideas and show a hands-on demonstration using Leankon's NFC antenna as example. The first question is, what's the NFC or near-field communication? It is a short-range wireless technology that works at 13.56 MHz. It lets two devices communicate simply by bringing them close together, usually just a few centimeters apart. Because of that short range, NFC is perfect for secure data exchange and quick, contactless interactions. NFC technology is commonly used in our daily lives, such as contactless payments, transit cards, and access badges, and it's also used for device pairing, smart home control, and authentication. In short, NFC makes our daily technology interactions smoother, faster, and more connected. The NFC antenna, sometimes called the NFC coil, is one of the most important parts of an NFC system. It acts as a bridge between the NFC reader and the device, allowing both energy and data to flow between them. Usually, it's a small conductive loop that creates a magnetic field to exchange the data. The antenna serves three main purposes. First, it handles energy transfer, collecting energy from the reader's electromagnetic field to power passive tags. Second, it manages data transmission, sending and receiving signals at 13.56 MHz for secure communication. And third, it shapes the field and sensitivity. Its size, shape, and placement determine how strong and stable the NFC link will be, even near metal surfaces. To demonstrate how antenna design affects performance, we're using the ST25R3911B evaluation board together with a Leankon NFC antenna. When designing antennas, designers often run into challenges like physical limitations, impedance mismatches, and the influence of nearby components on the antenna's magnetic field. In this session, we'll focus on how to fine-tune the antenna impedance so it resonates precisely at 13.56 MHz, the key frequency for optimal NFC communication. Every NFC chip manufacturer has a target impedance that gives the optimal performance and energy efficiency. To find those values, as you can see that we use ST's online design tool, which calculates the antenna's impedance using parameters from the antenna datasheet. The tool makes the design process much easier. It automatically generates matching component values that bring the antenna close to the ideal resonance point. This helps engineers save time and achieve initial antenna impedance right from the start. Before measuring the antenna's impedance, it's essential to calibrate the vector network analyzer, or VNA. Proper calibration ensures that all measurements are accurate and reliable. Without that, the results may not represent the antenna's true performance, leading to incorrect matching values and unpredictable system behavior later on. So, the careful VNA calibration is the foundation of trustworthy impedance testing. After completing the VNA calibration, we measured the antenna's impedance by using the recommended matching values from ST company. The results showed that the resonance frequency was slightly lower than expected, meaning that further optimization was still required. Both the S11 curve and the Smith chart clearly illustrate this shift, showing that a few fine-tuning adjustments are needed to reach the target 13.56 MHz resonance point. To evaluate the antenna's real-world performance, we tested its detection distance using 5 different NFC forum tags. A precision test fixture with a built-in ruler was used to make sure all measurements were accurate and repeatable. We can see the test data are presented in the table, which shows the baseline detection distances. Overall, the performance is not bad, providing a solid foundation for further optimization. Next, we fine-tuned the matching components step by step, adjusting the matching values until the antenna's resonance frequency aligned closely with the ST target impedance. This iterative optimization process helped us minimize mismatch loss and achieve stable resonance at 13.56 MHz, ensuring the antenna operates at its highest efficiency. After optimization, the antenna showed a significant improvement in detection distance across all 5 NFC forum tags. Each tag achieved a longer detection range compared to the baseline measurements. These improvements confirm that proper impedance matching plays a key role in maximizing NFC system performance. As such, we can clearly see that proper impedance matching plays a vital role in overall NFC system performance. Through careful optimization, we achieved detection distance improvements ranging from 16 to 43 millimeters. These enhancements lead to better system reliability, a more consistent user experience, and improved energy efficiency, which together result in longer battery life for NFC-enabled devices. To help accelerate NFC product development, Leankon offers a wide range of off-the-shelf NFC antennas. These solutions enable designers to achieve faster integration, optimized performance, and reduced time to market for NFC-enabled products. Thank you for joining us on this exploration of NFC antenna design and optimization. For more information, visit our website or contact us directly.